all over the world, and the mission is providing scientists the most extensive observations of a comet in history. Well, today is part 2, the science. You'll hear brief presentations, then we will open it up for questions. Let me introduce you to today's presenters. First up will be Michael Ahern, epoxy principal investigator, University of Maryland, College Park. Pete Schultz, epoxy scientist, Brown University. Tim Lawson, epoxy project manager in the Jet Propulsion Laboratory in Pasadena, California. And Jessica Sunshine, epoxy deputy principal investigator, also from the University of Maryland. But before we get started, it's my pleasure to invite to the podium Dr. Jim Green. He is the director of NASA's Planetary Science Division, and he has an incredible amount of planetary launches, missions, such as epoxy and other activities that are on the horizon. He's going to set the stage, put things in context. So, ladies and gentlemen, welcome Jim Green.
Well, it's really a great pleasure at this time to be able to talk about some of the scientific results from a fabulous mission. But before we do that, I thought I'd give you a little background. In January 2005, the Deep Impact mission was launched. And by July of that year, its impactor hit a comet, Tempel 1, and evacuated the top layer surface. And that mission was designed to be able to look at the below surface composition and was a tremendous success. Upon the completion of that encounter, the spacecraft was in excellent health, it had plenty of fuel, and a new mission was devised and approved by NASA headquarters. And that mission was named EPOXY. Now, the reuse of this particular spacecraft at a fraction of the cost that it would take to build a new one is just a tremendous bargain for NASA, the science team, and the nation. And as Dwayne mentioned, on November 4th, just 2 weeks ago, EPOXY flew by another beautiful comet, Hartley 2. And by the end of the day, a press conference was held and talked about those initial results. However, it's only been over the last 2 weeks when the science team has actually had the detailed opportunity to sit down and look at the observations and come to some consensus and dig into the data that we're here to hear about today. There's some tremendous results that they're going to present, some astounding images that we will see. And without further ado, let me turn it over to Michael.
Thanks, Jim. Today we're going to talk about the ice that is spewing out of Comet Hartley 2. When we excavated 10,000 tons of material from Comet Tempel 1 5 years ago, we looked really hard for the chunks of ice that we thought we would be excavating, and we didn't find any big chunks of ice. Most of the water came out as ice, but it was all in tiny micron-sized grains. So when we saw the images come down, even in real time in the raw data, and realized we had a cloud of snow around the nucleus, we were astounded because it was so different from Comet Tempel 1. And it's driven by a large excess of dry ice in at least one end of Comet Hartley 2 and possibly in the other end as well. The first image shows an example, and many people will know that our high-resolution instrument is slightly out of focus, so we have to process the image in order to resolve the details that should be there, and that's in the next image. And here you see a lot of things. You see lots of detail on the nucleus. We can trace individual jets down to discrete features on the surface of the comet. But and we can also see that there are jets clearly coming from features on the night side of the comet in darkness. Now that's an important result, but today we're not going to focus on the nucleus. We're going to focus on that swarm of points around the nucleus. Those are not stars. Those are all chunks of ice. And to focus on those, the next slide is just off the edge of the nucleus. Again, this is the image before we manually process it to fix the focus. In geek speak, it's a scene-dependent iterative deconvolution, but basically we just process the image to fix the fact that it's out of focus. And the next image is in focus. Every one of those pinpoints is a chunk of ice. It's just a point of light to us, so we can't measure the sizes directly, but indirectly, just from the brightness, we think the biggest ones are at least the size of a golf ball and possibly up to the size of a basketball. They'll probably be very porous. And for the details of where they are and how they're moving around, I'll hand over to Pete Schultz.
Thanks, Mike. I mean, when I see that image, it just looks like a snowstorm, and that's what I want to tell you about. I want to find out I want to show you how we found out what these were, how these were, we detected they were snowballs, where they are, and we wanted to find out what they mean. So if I can have that first closer look. This shows a close-up look where you see on the left-hand side is that blurry image from the defocused instrument of the high-resolution imager. On the right, it's in focus now through that deconvolution, and I've identified some of the streaks. The bright ones are identified in red, the faint ones are identified in blue, and then the small specks that you see are circled in yellow. So there's an assortment of different things we see when we look at very high resolution. And what these are really indicating, these streaks are telling us that, in fact, it's related not to their motion, but the motion of the spacecraft. We're going 27,000 miles per hour, and as we're whizzing by this nucleus, we're seeing these features. The longer the streak, probably the closer it is to the spacecraft. The fainter it is, probably the farther away. So we're already getting a sense that we're seeing a lot of material in the field of view. So let's take a different view, and this is now the medium resolution imager. And on the left, you'll see this context view. And that's kind of important because you see this long shadow cast by the nucleus on the inner coma. And that's dust because you can't cast a shadow in space. It does cast it on the dust. But if you look at the right, you'll notice that there are, again, all these specks. And this is in the medium resolution imager. So the question is, which ones are actually stars? Which ones are dust? And which one are artifacts? And so to do that, we need to take one more step. And so in the next time step, I'll show you a flicker movie. And this flicker movie allows you to see things in motion. And when we first saw this, our mouths just dropped. Our whole team just dropped. Because we can begin to see, if you look very close to the nucleus, you can see things that are slowly moving, but then as you go farther away, they're really migrating. This is telling us that there's depth. Yeah, and so we are seeing now with this imaging, we are now seeing two different instruments, the high resolution and the medium resolution. We're seeing them with two different instruments, and we're seeing the same objects. To me, this whole thing looks like a snow globe that you're just simply shaking and watching it fly. So now the question is, where are they in space? And to see that, we've got to go to this next time step, where here we actually track out particles. And so you notice that red one just zipping by. And this is kind of like being in a car and with the signs just flying right by you, with the other ones in the distance, like the trees in the distance, staying pretty steady. So this gives you a sense that we are seeing things from different distances away. And the importance of this is that we can actually locate these objects, and we might be able to tell where they are with respect to the nucleus in space. Now, we now know that these particles, as they're moving, are still going less than about a meter per second. So they're not going very fast. Again, it's really the spacecraft doing the moving for us. So with that, it also tells us that we're seeing displacements. And when you see displacements, you can see things in stereo. So if you will, please put on your stereo glasses, and we'll take a look. We'll go down into 3D. I love this look. Now, be sure, first of all, that the blue filter is on your right and the red is on the left. And I also suggest that if you're looking at this on TV, move back to the monitor, because I think that'll help you see this better. Notice that this is a slightly different orientation. We have to do this because the stereo is constructed by the motion of the spacecraft. And now the sun is really at the top. Now, I've circled some of the particles, and as you look at these particles, even without stereo glasses, you can see the depth. Some of the ones that are near the nucleus are pretty far back, or actually kind of sticking out in front. And then over to the left, you'll see some that are staying way in the back. And for those of you who don't have stereo glasses on, You can do this later, but you can see that there are some of these specks, the green and red are far apart. Those are the ones that are close to us, and those that are not far apart are the ones behind. So we can still clearly see in this case, just like with the streaks, that there's some way in the foreground, some way in the foreground. So these objects are really surrounding the nucleus, and now we have kind of this estimate of size, which Mike suggested somewhere between a couple of inches to as large as a couple of feet. But we have the distribution as well. The team members have estimated that for every 10-inch particle you might see, there'd be 1,000 of the 1-inch particle. So there's a whole range. So when I look at this image, especially in 3D, this whole thing kind of appears to me as if this nucleus has a posse of many comets surrounding it. So Jessica will describe how these things are lifted off the surface when she talks about the process. But now let me pose a different question, which is, could any of these actually hit the spacecraft? So if we go to the next time step, here's an image of us approaching. Now, as you see those two streaks that are circled, realize that those are 3 times closer to the spacecraft than they are to the nucleus. And you also realize we're heading toward the comet, at least offset from the comet. And that raises the question, did we get hit? Should we be concerned? And so with that, I'll turn it over to Tim.
Thanks, Pete. So talking about flying through this field of ice chunks and snowballs and other hazardous objects for the spacecraft, first I want to remind you what our flyby geometry was. If you roll the animation, it'll show you a rendering of what the flyby looked like as the spacecraft approached a comet and went by it, and then it'll be followed right after that by the view of the comet that we had from the spacecraft imagers. And just reminding everyone, we flew by the comet at a distance of about 435 miles. We flew by it at a speed of about 27,000 miles per hour, and the spacecraft was slightly below the comet in the sunplane, and that produced the views that you'll see here. So as we look back and try to figure out whether or not the spacecraft was damaged at all or whether we're hit by any of these particles, first order look, you can look at the health data and all the telemetry from the spacecraft to tell whether everything is still working fine after the flyby. And that data we got down very shortly after the flyby. The first set of data we brought back were telemetry files before we started bringing pictures down. And so we were able to tell right away that we went past the comet through the coma without any kind of discernible damage to the spacecraft. All the instruments and all the equipment on board the spacecraft was working just fine. So then the next step is to try to figure out whether or not we might have gotten hit by any small particles that we could detect. And so to talk about that, I'd like to refer to this model of the spacecraft. If you look at this model here, if you imagine being hit in a part of the spacecraft that's away from the center of mass, you can imagine that imparting a little bit of torque to the spacecraft and moving it. And so those are the kind of clues that we'd be looking for. And so the team undertook a pretty detailed examination of the attitude data on the spacecraft. We have 2 different ways of sensing the attitude of the spacecraft and looking at both sets of data, trying to pick out, get rid of the noise and look at real attitude excursions. That gives us an idea of where the spacecraft might have moved as we went through the flyby sequence. Then you have to take and rule out any movements that are due to things going on the spacecraft. For example, receiving position updates from the AutoNav software, filter wheel movements can be sensed in the attitude data, and even the IR scans as the spacecraft would move back and forth to perform the IR scans. All of those things you have to rule out because that obviously then would not be a dust hit. So after doing that and going through a fair amount of detailed analysis, we've identified 9 events in the 10 minutes around closest approach that could possibly have been dust hits. Once you identify those, then you have to try to bound, well, what size particle was it that might have hit us? And so for that, you have to make some kind of assumption. The assumption that we used in this analysis was basically assuming something that hit the spacecraft about a meter away from the center of mass to try to bound the size of the particles. Based on that, we estimate that these 9 events, the particles that hit us, looking at the attitude excursions that we saw, ranged from about 0.02 to 0.2 milligrams in weight. 0.2 milligrams, that's about the weight of an eyelash. So you can imagine something that small, that light hitting you and causing an attitude disturbance. Well, traveling at those kind of velocities, you can impart a fair amount of energy when you hit an object with that. So that's based on our analysis and the telemetry we have from the spacecraft, we can conclude that, yes, we may have been hit by some of these small particles, but none of them were large enough to cause any damage to the spacecraft. That's an important point here. I'd also like to emphasize the point that November 4th wasn't the end of the story for this flyby. We're still continuing to collect data. We've collected about 32,000 images of the comet since November 4th. We continue